The trip time for a fuse or circuit breaker depends greatly on the device's specifications and its trip curve characteristics. Typically, a higher current leads to a faster trip time. Most fuses and circuit breakers are engineered to trip within seconds when the current significantly exceeds their rated capacity. For instance, consider a 4000 amps fuse or circuit breaker, where the rating is at 80% of the load, meaning it's designed for 3200 amps. If the current hits 4000 amps, it's expected to trip almost instantaneously. It's highly improbable that it would take 3 IOs to trip at this specific current level. Trip time curves offer insights into how long a device will take to trip at various overcurrent levels. However, keep in mind that these curves are usually available for current far exceeding the device's rated capacity. When the current is near the rated capacity, the trip time is generally much quicker than what you might see on the trip time curve. To know the actual trip time characteristics, it's essential to refer to the manufacturer's specifications for the particular fuse or circuit breaker you are using. The specific trip time depends on several factors. Firstly, the type of overcurrent device plays a crucial role. Fuses and circuit breakers operate differently, and their trip time characteristics vary. Secondly, the specific design and construction of the overcurrent device influence its trip time. Different manufacturers employ varying technologies and materials, resulting in diverse performance characteristics. Thirdly, the magnitude of the overcurrent significantly affects the trip time. Higher overcurrent levels typically lead to faster trip times, while lower overcurrent levels may result in longer trip times. Fourthly, the ambient temperature can also impact the trip time. Higher temperatures may cause the overcurrent device to trip faster, while lower temperatures may slow down the trip time. Fifthly, the history of the overcurrent device can affect its performance. Repeated exposure to overcurrent events can degrade the device's ability to trip accurately and reliably. Fuse characteristics are important to understand. Fuses are designed to melt and break the circuit when subjected to an overcurrent condition. The trip time of a fuse depends on the fuse's construction, including the type of metal used in the fusible link and its dimensions. Fuses are typically classified into different categories based on their speed of response, such as fast-acting, medium-acting, and slow-acting fuses. Fast-acting fuses are designed to trip very quickly, typically within milliseconds, to protect sensitive electronic components from damage. Medium-acting fuses offer a balance between speed and surge current withstand capability, making them suitable for general-purpose applications. Slow-acting fuses are designed to withstand temporary surge currents without tripping, making them ideal for protecting motors and other inductive loads. Circuit breaker characteristics are similarly important. Circuit breakers are electromechanical devices designed to trip and interrupt the circuit when an overcurrent condition occurs. The trip time of a circuit breaker depends on the breaker's design, including the type of trip mechanism and its calibration. Circuit breakers typically use one of two trip mechanisms, thermomagnetic or electronic. Thermomagnetic circuit breakers use a bimetallic strip that bends when heated by an overcurrent, causing the breaker to trip. Electronic circuit breakers use electronic components to sense the overcurrent and trip the breaker. Electronic circuit breakers offer more precise and adjustable trip time characteristics compared to thermomagnetic circuit breakers. Factors influencing trip time curves are the rated current, which is the maximum current that the device is designed to carry continuously without tripping. The overcurrent level is the amount of current flowing through the device in excess of its rated current. The ambient temperature surrounding the device and the device's history of exposure to overcurrent events. Consulting manufacturer specifications is critical. The manufacturer's specifications for a fuse or circuit breaker provide detailed information about its trip time characteristics. These specifications typically include a trip time curve, which plots the trip time of the device as a function of overcurrent level. The trip time curve is an essential tool for determining the expected trip time of the device under different overcurrent conditions. In addition to the trip time curve, the manufacturer's specifications may also include other relevant information, such as the device's interrupting rating, voltage rating, and operating temperature range. The interrupting rating is the maximum fault current that the device can safely interrupt without being damaged. The voltage rating is the maximum voltage that the device is designed to operate at. The operating temperature range is the range of temperatures within which the device is designed to operate reliably. Practical considerations include the selection of appropriate overcurrent protection devices is a critical aspect of electrical system design. Overcurrent protection devices must be carefully selected to ensure that they can protect the electrical system and its components from damage in the event of an overcurrent. The selection of overcurrent protection devices should be based on several factors, including the rated current of the circuit, the expected overcurrent levels, the type of load being protected, and the applicable codes and standards. Coordination of overcurrent protection devices is also important to ensure that the devices trip in a coordinated manner, minimizing the extent of the outage in the event of a fault. Coordination involves selecting overcurrent protection devices with different trip time characteristics so that the device closest to the fault trips first, isolating the fault and preventing it from propagating to other parts of the system. Regular testing and maintenance of overcurrent protection devices is essential to ensure that they are functioning properly and will trip when needed. Testing should be performed according to the manufacturer's recommendations and applicable codes and standards. Maintenance should include visual inspections, cleaning, and replacement of damaged or worn components. Real-world examples are helpful. Imagine a motor circuit with a 20-amp circuit breaker. If the motor draws 25 amps due to a fault, the breaker should trip relatively quickly, within seconds or minutes, depending on its trip curve. If the motor draws 40 amps, the breaker should trip much faster, potentially within milliseconds. Now consider a high voltage distribution system with a 1200 amps fuse protecting a transformer. If a fault occurs on the secondary side of the transformer, resulting in a current of 6000 amps, the fuse should trip almost instantaneously to prevent damage to the transformer and other equipment. In summary, understanding the trip time characteristics of fuses and circuit breakers is crucial for ensuring the safety and reliability of electrical systems. By consulting the manufacturer's specifications, considering the factors that influence trip time, and following best practices for selection, coordination, testing, and maintenance, engineers and technicians can ensure that overcurrent protection devices provide adequate protection against overcurrent events. Remember that the 80% rating often refers to the maximum continuous load allowed on a breaker or fuse, not a direct percentage of the instantaneous trip current. Continuous load should not exceed 80% of the breaker's rating. The actual trip time for an overcurrent event significantly exceeding the breaker's rating will be much faster than what might be inferred from a continuous load rating. Always consult the manufacturer's data and trip curves for accurate trip time information. The concepts of inverse time curves are essential to understanding the behavior of fuses and circuit breakers. These curves illustrate the inverse relationship between the magnitude of the overcurrent and the time it takes for the device to trip. In other words, as the overcurrent increases, the trip time decreases, and vice versa. The shape of the inverse time curve is determined by the design and characteristics of the overcurrent device. For fuses, the curve is typically determined by the melting time of the fusible link. For circuit breakers, the curve is determined by the characteristics of the trip mechanism, such as the thermal or magnetic elements. The inverse time curve is an essential tool for coordinating overcurrent protection devices. By selecting devices with different curve shapes, engineers can ensure that the device closest to the fault trips first, minimizing the extent of the outage. The NEC, National Electrical Code, provides guidance on the selection and coordination of overcurrent protection devices. NEC Section 240 covers overcurrent protection requirements for various types of electrical systems and equipment. NEC Section 240.4 specifies the requirements for protecting conductors against overcurrent. NEC Section 240.6 lists the standard ampere ratings for fuses and circuit breakers. NEC Section 240.12 provides guidance on the coordination of overcurrent protection devices. Consulting the NEC is essential for ensuring that overcurrent protection systems comply with applicable safety standards. In industrial settings, overcurrent protection is critical for protecting motors, transformers, and other expensive equipment. Motors are particularly vulnerable to overcurrents caused by overloads, short circuits, and ground faults. Overcurrent protection devices for motors must be carefully selected to provide adequate protection without causing nuisance tripping. Transformers are also susceptible to damage from overcurrents. Overcurrent protection devices for transformers must be coordinated with the transformer's thermal withstand capability to prevent overheating and insulation breakdown. In residential settings, overcurrent protection is essential for protecting branch circuits in appliances. Branch circuits are typically protected by circuit breakers, while appliances may be protected by fuses or circuit breakers. Overcurrent protection devices in residential settings must be selected to provide adequate protection against overloads and short circuits without causing nuisance tripping. Newer technologies in overcurrent protection include arc fault circuit interrupters (FSIs), which are designed to detect and interrupt arc faults, which are a common cause of electrical fires. Ground fault circuit interrupters (GFCIs), which are designed to detect and interrupt ground faults, which can cause electric shock. Solid-state circuit breakers, which use electronic components to sense and interrupt overcurrents, offering more precise and adjustable trip time characteristics compared to traditional electromechanical circuit breakers. Furthermore, advancements in fuse technology have led to the development of current-limiting fuses, which are designed to interrupt high-fault currents very quickly, limiting the amount of energy released into the system and reducing the risk of damage. Self-resetting fuses are another innovation, allowing the circuit to automatically restore power after the overcurrent condition has been cleared, improving system uptime and reducing the need for manual intervention. Also, adaptive overcurrent protection systems utilize advanced algorithms and communication technologies to dynamically adjust the trip settings of overcurrent devices based on real-time system conditions. These systems can improve system reliability, reduce nuisance tripping, and optimize protection performance. To summarize key takeaways, fuses and circuit breakers are critical components of electrical systems protecting against overcurrents. The trip time of these devices depends on various factors, including the device's design, the magnitude of the overcurrent, and the ambient temperature. Consulting the manufacturer's specifications and understanding inverse time curves are essential for selecting and coordinating overcurrent protection devices. The NEC provides guidance on overcurrent protection requirements. Regular testing and maintenance are crucial for ensuring that overcurrent protection devices function properly. Finally, ongoing advancements in technology are leading to the development of more sophisticated and effective overcurrent protection solutions.